and welcome back. A question. Who built the first binary counter that went on to be the basis of modern computing, helped discover the neutron, worked on radar, and built components for one of the world's earliest computers that cracked the German Enigma Code? I had no idea who that could be until Gareth Wynn-Williams, a family friend, an astrophysicist, and an astronomer, told me about his dad. We've known Gareth's family for many years, both from Hawaii and in Cambridge, England. Gareth is an astronomer and full of fascinating stories. One day, while visiting us here in France, he told me about his dad. As a science filmmaker, I had to bring the story of Gareth's dad to you, the man who invented scale of 2 counting.
In our laboratories today, we live in an atmosphere dim with the flying fragments of exploding atoms.
Cambridge was a big international centre for the study of the structure of atoms. My father's contribution to this work was his skill at devising electronic instruments.
Progress in our knowledge of the mechanism of these transformations became more rapid when powerful electric methods were developed to count automatically the swift particles ejected during these nuclear explosions.
Unsung heroes become sung heroes, provided you get the right publicity. One tends to associate things with the big names who are quite justified, have got these strong reputations, but they cannot make the discoveries without the work of the workers in the field.
My father's secretary was used for one of the most famous discoveries in the Cavendish Laboratory, which was James Chadwick's discovery of the neutron.
We are witnessing today the rise of a new department of fundamental knowledge.
When the Second World War broke out, he was recruited to apply his skills with electronic counting to decode messages distributed by the Nazis.
Cambridge, of all England, the shire for men who understand.
I am Gareth Wynn-Williams, the son of Charles Errol Wynn-Williams.
And a traveller new to this ancient county and the other East Anglian villages that border it might ask just what it is these quiet people understand.
Well, I grew up in London and went to university in Cambridge, got a degree in physics, and then I spent a year in Kenya teaching in the physics department of University of East Africa. This was under the VSO scheme, which is a bit like the American Peace Corps scheme. I then came back to Cambridge and joined the radio astronomy group, which was part of the Cavendish Laboratory there.
Here, knowledge is far from silent. Here, too, are the men who understand and who always want to understand more. They jab at the frontiers of knowledge like the spear point of an army. And since Cambridge University began nearly 7 centuries ago, they have been probing those frontiers, casting doubt on old ideas, asking awkward questions. They still ask them today.
My father was born in 1903 in Swansea in South Wales, but he grew up in Wrexham in North Wales. His father, called William Williams, was a scientist himself. My father, called Charles Errol Wynn-Williams, though his family always followed the Welsh custom of using your second Christian name. So he was, to his family, he was Errol Wynn-Williams, though professionally he always just signed himself as C.E.Wynn-Williams for Charles Errol Wynn-Williams. He went to the University of Wales at Bangor in Carnarvonshire in North Wales for his undergraduate degree, did very well at that, and got an admission into the University of Cambridge to do his PhD. He got a connection with Trinity College, which happens to be the college that I went to later on. His PhD supervisor and guide was Ernest Rutherford, one of the most famous scientists in physics. His real interest was in designing tools for doing research rather than getting heavily involved in the theoretical side of physics.
The product of this magic lamp we call a vacuum tube is not light, but electricity. Electrons set free from the atoms of matter that hold them captive. And the world and all it contains are built of atoms. Yet hidden in every single last atom is from 1 to 92 electrons. This wire, like everything else, is composed of atoms. And if microscopes could magnify 10 million times instead of paltry thousands, one of these atoms probably would appear as a tiny elastic sphere. A sphere formed by negatively charged electrons swarming around a massive nucleus of positive electricity.
Electronics was based almost entirely on what we call vacuum tubes. These were things that were like, they looked like light bulbs. Electric currents were passed through the vacuum in the tubes and could be controlled by electrical means. These were the basis of radio sets. They were a part of the rise of what we now refer to as electronics. And my father developed his skills very quickly in that.
I think we can say that the Cavendish Laboratory from the period of around about 1897 around to 1932 was absolutely central to the understanding of the nuclear structure of the atom. J.J. Thomson discovered the electron in 1897, and then Rutherford, who had been in the Cavendish but then by the later stages was at Manchester, carried out the beautiful work on the discovery of the nuclear structure of the atom. That was complete. The experiments were completed around about 1911. Then Rutherford came back to Cambridge in 1919 and brought with him the new experiments that he'd been working with Chadwick in Manchester on the disintegration of nuclei. He called it disintegration. In fact, what it was the transmutation of one element into another, the philosopher's stone, if you like, in becoming a reality in the 1920s.
At the time my father moved to Cambridge, Cambridge was the big international centre for the study of the structure of atoms. My father's contribution to this work was his skill at devising electronic instruments. And the reason why these are important was that the kinds of experiments that were being done often involved firing charged particles at atoms and then watching the way that they were deflected. There were already existed devices that could collect that charged particle and generate a small electrical pulse. So a lot of the experiments involved trying to count these electrical pulses as they were produced by the experiment. One of the first things he did was developed a circuit that raised the strength of these little pulses. It was really a kind of a very sensitive electronic amplifier to make the pulses easier to measure. But by far my father's most important contribution was to build the first electronic counting system.
The development of the electronic counter is a fabulous story. Earlier, people had been counting with mechanical counters, but they could not get the rates that were needed to detect the particles. The way that this was done was by looking at the events appearing on a fluorescent screen. And in order to get accurate results, one had to set up extremely strict protocols about the procedures to be used for counting. Now, these procedures were set out in the books written by Chadwick and Rutherford, and they're complex, and they take a great deal of care to make them work. When the results were announced of the nuclear decay processes that had been discovered by Rutherford, then there was doubt about the reality of some of their results, and there were disputes, a serious dispute between the Vienna physicists and the Cambridge people. And the root cause was the subjective nature of the counting of particles, which was then to be replaced by the more objective means of using the electronic counters, which took out the human element. So the development of the electronic counters was absolutely crucial for being able to get absolutely accurate counting rates for the decay process which they were studying.
Mechanical ways of counting these pulses involved electrical relays, which are metal-made switches where the switches pull by a little magnetic coil. And as you put a current through the magnetic coil, you can then switch a voltage off and on. And these things were used, for example, in early experiments in telephone exchanges. But the trouble is that these electromagnetic relays are slow. You actually need to have a pull from a magnet to accelerate the switch that then turns the electric current off or on. So the speed was very much limited. My father's most important contribution to physics at this time was the development of the world's first electronic counting circuit. Electrical pulses were counted by a circuit using electronic tubes. In fact, I can't say vacuum tubes because these were things called thyrotrons, which looks like a vacuum tube but contains a very small amount of gas. These were devices introduced as a kind of electronic switch. And my father realized if you had a number of these thyrotrons and you devised the right kind of circuit, you could have electrical pulses being counted by these thyrotrons. My father's group received a donation of 6 thyrotrons by a company called BTH. And we have to remember that at this time the Cavendish Laboratory had an extremely small budget for equipment. And my father realized that he only had 6 of them. He needed to use them in the most efficient way he could. He realized that the most efficient way of doing this was to count using the binary system. In normal life, we use what's called the decimal system. We count in ones, and then we count in tens, and then we count in hundreds, then we count in thousands, etc., etc., etc. Now the binary system counts in ones, then in twos, then in fours, then in eights, then in 16s. My father realized the advantage of the binary system is you can count bigger numbers with the same number of thyrotrons. And this is an enormous breakthrough because all modern computing systems are based on the binary system. He didn't use the word binary, he used the word scale of 2 counter. The reason why my father was encouraged to develop this counting system, to get accurate measurements, you need to measure a large number of deflections. If you had these electrical switches, the relays, you had to kind of slow things down so that not more than a few per second were ready to be counted. By building this electronic counting system, you could have more data, therefore your data could be more accurate. So it made a big improvement in the quality of the data being obtained by these experiments. My father's circuitry was used for one of the most famous discoveries in the Cavendish Laboratory, which was James Chadwick's discovery of the neutron. Chadwick used the scale of 2 counter for establishing the existence of the neutron. Nowadays we're used to electronics being extremely small. The scale of 2 counter with the batteries that were required to run it occupied most of a cart. One of the requirements to make the experiments work successfully was that they should not be disturbed. And this led to my father building a notice above his device that said, "Talk softly, please." This was in effect aimed at Lord Rutherford, who a very distinguished man, but he did have a very booming voice. I don't know if Rutherford realized it was directed directly at him.
In our laboratories today, we live in an atmosphere dim with the flying fragments of exploding atoms. And on this occasion, I wish to say a few words on the methods and ideas employed to break up atoms and to realize, if even on a small scale, the old dream of the alchemists of transmutation of one element into another. This is a problem in which I have been personally engaged during the greater part of my scientific life. And during this time, I have witnessed an astonishing increase of our knowledge. Progress in our knowledge of the mechanism of these transformations became more rapid when powerful electric methods were developed to count automatically the swift particles ejected during these nuclear explosions.
My father spent 10 years at the Cavendish Laboratory, and in 1935 he was offered a faculty position at Imperial College London, and he worked for a while with the nuclear research that was going on down there with G.P. Thomson. When the Second World War broke out in 1939, he was recruited to help run the radar stations that were being built around the coast of England. These were large towers that sent out radio pulses with the idea that these radio pulses would be reflected off the front of incoming aircraft. And he used to drive from radar station to radar station, helping them get these things working to their top specification. When I was born in 1944, for most of my childhood years, in fact until I was a teenager, my father led me to believe that he had spent all the war working on these radar stations, which made sense. My father was an expert on electronics. Radar stations have large amounts of electronics. When my brother and I were young, we used to take holidays in North Wales. In fact, usually in Llandudno, where my father's sister, Marjorie, had a house. And to get to North Wales in our car, which was a Hillman, 1935 Hillman Minx, we used to drive up the A5, one of the roads actually dating back to the Roman times. And this was in our Hillman car, which could just reach a maximum speed of 45 miles an hour. We would often take a break around Bletchley, which is a 2 hours drive from London. And it was only in the 1970s, because a book was published that concerned the British code-breaking activities that were taking place in London. I read this book and a couple of things jarred with me. And one of them was the fact that the book described the main centre of code breaking in wartime England as being in Bletchley. I realised, I noticed my father seemed to know his way around Bletchley. I can't remember the details, maybe it was he knew where the restaurants were. And so when I read this book about the code breaking, I challenged my father. I said, "Did you have anything to do with this?" And he ummed and ahed and didn't give me an answer for a while. And I realised afterwards he must have still had some kind of contact with the British Secret Service and must have called them up and asked them whether it was okay to say anything. So my father was recruited sometime during the war, I don't know exactly when that was, to apply his skills with electronic counting to the efforts that were being made to decode messages distributed by the Nazis. And my father was called in to try to apply his electronic skills, particularly with counting circuits, to this effort. And he spent most of his time working not at Bletchley itself, but at a place called the Post Office Telecommunications Centre, which is in Dollis Hill in North London. My father's work at Dollis Hill led to the construction of what some people think of as the first electronic computer, which was a device called Heath Robinson. And this was designed to try to decode these German messages. The machine was not purely electronic. It involved large strips of paper tape that had holes in it that could contain information. As these paper tapes spun around on their various axes and the pulses were read, as my father's scale of 2 counting device, or something based very closely on that, was used to count the pulses coming in as these 2 paper tapes would be compared. This whole device was referred to as a Heath Robinson. Now, Heath Robinson was a cartoonist who produced wonderful cartoons of interesting devices. And I remember as a child that we had this annual in our house, and I remember enjoying it. And I suspect that the fact that when this first book came out about Bletchley, the fact that it referred to Heath Robinson rang a bell in my mind that my father owned a book about Mr. Heath Robinson. And I think that was one of the things that triggered me to challenge my father on this. My father got married to my mother in 1943, at the time that my father was working on code breaking. He did have a car, so if he'd been visiting my mother and was about to set off back to where he was working, and just to make it quite clear that she didn't know where he was going, she told me that he asked her to specify whether he left the house driving to the left or left the house driving to the right, so there could be nothing revealed from his departure direction. At the end of the war, my father went back to his position in Imperial College and worked on nuclear research programs for a while, but his real strength was in physics education. His main work at Imperial College was running the experimental physics labs for the undergraduates, and so devising instructive, interesting, challenging experiments was very much in his field, and he introduced a lot of great work in that area.
The way in which science advances is by making discoveries and then following up the discoveries. And you need a culture, an environment which encourages that sort of approach. And you never quite know where the next great discovery is going to come from. So, for example, take the discovery of pulsars, for example. That was a complete surprise. Nobody would have thought of looking for neutron stars by that method. And so what you must be working is to create an environment, a creative environment, where the people are addressing at the very limits of technological capability what are perceived to be the key issues. And they need not be the things which everybody else is working on. So long as you're working on the areas where you're making an order of magnitude increase in capability, that's where you're going to make the discovery. And I believe that the reason that my book on the history of the Cavendish Laboratory is called Maxwell's Enduring Legacy was that he said famously that although some people say that all that physics needs to do now at the end of the 19th century is measure the constants more accurately, Maxwell made the profound remark, it's by making that order of magnitude improvement in how you understand existing physics that you discover the next generation of physics. And that's the way it works. It's you're always pushing the technology to explore areas of parameter space you've not been able to go before, and you will always find something new.